Onu da belirtmiş olayım. Herkes bilsin diye. Kayıt başladı sanırım. Okey. רוני, בוא נתחיל אם אתה מוכן. עכשיו תורך.
Okay. So, too bad I can't be with you in Turkey. So you're in Mersin?
Yes, yes.
Oh, that's a nice place.
Yes, close to Cyprus and Israel.
Yeah, I've been there and I would like to be there now, but maybe it's rainy, probably. It's rainy a little bit.
Yes, it's rainy here too.
So we'll wait for the summer, hopefully.
But without telling you, you are always invited, Ronnie. And before starting, please pass my greetings to your beautiful wife, Yafa.
Thank you. And what I want to tell you today about thermodynamics of quantum engines, and I hope it will be interesting for you. And okay, how does this work? Here. And these are people I want to thank that I worked with. And it starts from Eitan Geva, who was my first graduate student on the subject. And here Ro'i Dan is the current graduate student, and many people contributed, and you can see them here. And so this is I would say, many years of work on the subject. Okay, so the point about thermodynamics, you can think how it started, and the motto is learning from example. And here we see Sadi Carnot, and extracts from his book. So he has only one publication. This book, you say, Reflections on Poussin's Motrice, or motive power of engines. And the point is that he was unliked by the environment in France. His father supported Napoleon, and he was an engineer in the army, so he was sent to exile to some fort, but he was able to write this book, which you could say revolutionized science. And it was published by his brother. And what's interesting when you read this book, it's very analytical. And you could say he's an engineer by training, or a military engineer, but the idea is universal. So the main idea in his book is universality. And what I want to show you here, that the motive power, or you can say the efficiency, depends only on the temperature of these sources. Here, you have it out of the book in a translation to English. The driving power of heat is independent of the agents used to realize that. And this will be a motto also for what I want to describe, that also you'll see that quantum engines work according to this principle. So from Carnot, we jump to Einstein, to 1905. And Einstein writes this paper here. You can say that one of his famous papers in 1905. You can say in the German journal, Annalen der Physik. And what we get out of it, you could try to follow how was Einstein thinking. So Einstein started from thermodynamics, and he thought about, okay, what should be the thermodynamics of light inside a black box? And he gets to this equation here, and he says this equation shows that the entropy of a monochromatic radiation of sufficiently low density varies with the volume according to the same law as the entropy of an ideal gas or that of dilute solution. So you could say here's mathematics, and the consequences of his insight here is that light is quantized. And you can say this famous relation E is h power n comes from this basically observation of the entropy of light inside the black box. Here we can see it here. You can, again, monochromatic radiation of low density within the range of validity of Wien's radiation formula behaves thermodynamically as if it is consistent of mutually independent energy quanta of magnitude. Okay, we doesn't even have, this beta here is h bar as we would know it today. So Einstein starts from thermodynamics and uses a consistency argument. And from this consistency argument gets to the idea that light is quantized. And once he reached the conclusion that light is quantized, he can get this famous formula that relates the energy to the frequency. And today, we wrongly interpret this paper as a photoelectric effect. But this is not correct because the photoelectric effect was only measured by Milik in 1913 and published 1914. So the idea is consistency. It's not that he was trying to explain an observation. He was trying to think about what the theory should tell us about the universe. And the main thing is that any theory should be consistent with thermodynamics. So this is Einstein and where he started. And we can go the opposite way, where you could say almost more than 100 years later. And we typically today, we know more quantum mechanics than thermodynamics, and we go the opposite direction. We start from quantum mechanics and we try to obtain thermodynamics out of our quantum mechanics formulation. And you could say that what we do is we find quantum analogs to system Bethe partition, the first law, second law, third law, and so on. So this is the motto that I'm going to follow here. So we have to build our thermodynamics from, you could say, quantum mechanics. So how do we do that? So I would say that in a certain case, a pioneering of what I'm going to describe today is Carnot efficiency of a 3-level amplifier. And the person responsible for this observation, which you could see the publication date is 1959, is Scoville. Was one of the inventors of solid state laser, and he worked at Bell Labs in the US. And as we saw already in Carnot, the substance that consists our engine is irrelevant. We should get the Carnot efficiency only depends on the temperatures of the hot bath and cold bath. So we can replace our working medium by a quantum mechanical working medium. And this is what Scoville did. And let's try to look at this analysis of, you can say, a 3-level laser or a 3-level amplifier. What do I have here? 3 levels, 0, the cold side and the hot side. I have a hot bath and a cold bath. So if I would be in your lecture room, I would have a laser pointer. This would be a flashlight of 6,000 Kelvin or something like that. My hot bath, and this would be room temperature. And you can say this hot bath equilibrates these 2 levels, the ground state and the upper level, and the cold bath tries to equilibrate these 2 levels. And if I set the things correctly, I get a population inversion between NH and NC, which I can couple to radiation, and I can get an amplifier out of it. So I can identify this radiation as work output, and the input is heat from the hot bath that gets dissipated to the cold bath to close this loop. And if you look at the model, I can say the population here, NC, is this Boltzmann factor with the frequency difference here. NH is the same Boltzmann factor with the frequency difference here. And I want to define the efficiency of this engine. So the input is omega h. This is the quant of energy I'm putting in. I'm getting out a quant of energy ni. So the efficiency is ni divided by omega h. And ni is this difference omega h minus omega c. I write it like that. And now I want to obtain the gain. So we know that for an amplifier to work, we need positive gain. So NH is bigger than NC. I can put this Boltzmann factors and their monotonic functions. I can get this inequality. Out of this inequality, I can get that the ratio of frequencies should be smaller than the ratio of temperatures. And if I put it into the efficiency definition, I get that this is smaller than the Carnot efficiency. And I get that the efficiency of this device, which we would call a laser quantum amplifier, this efficiency we'll later call an auto efficiency. So it's equivalent to the auto efficiency of our automobiles. So what Scoville got in this short paper is that the efficiency is bounded by Carnot efficiency, and you can get, if you have zero gain, you get an equality here. So this is a pioneering study that you could say connects a quantum device, a 3-level amplifier, with a Carnot engine. Now, what's missing here is dynamics. So this is what we want to put next into the story. And we want to put dynamics into thermodynamics. And the dilemma, which we do that, everybody in our day-to-day life has this choice. Here I have 2 cars that I can, you go to the dealer and you can buy either this, what is it, Porsche? No, it's, who can identify the red car? Or this Daisy efficient car. So you can say it's a Ferrari. If you want a Ferrari or this very fuel efficient car. So usually I take a pool. Personally, I would prefer a Ferrari, but what you know, that this is less efficient than this blue car that goes through these flowers. And the dilemma is, if I want power, I pay with efficiency. And if I want the most efficient, you can say engine, I'm going to get zero power. And this trade-off between efficiency and power, we'll see, is an important issue in this field of, you could say, quantum thermodynamics that we'll deal with, and especially when we think about engines. And there are 2 results that we know. You can say the maximum efficiency is bounded by Carnot efficiency, which is on the right. And what you have on the left is called the Curzon-Alboron efficiency. The truth is it was found before by Novikov, that the efficiency at maximum power is 1 minus the square root of Tc divided by Th, which is much more realistic estimate. And if you go to a power station anywhere and you ask, okay, what is the efficiency of the power station? And what I tell you is the temperature of the gas that goes in and you can say seawater, which is used to cooling. If you take this efficiency, the Curzon-Alboron efficiency, you'll get within 1 or 2% of the actual efficiency of the power station. And the Carnot efficiency is usually quite far off. So what it means that most of what we want is power and not so much efficiency. And from here, we want to build a quantum theory of a dynamical quantum theory, which I can describe my engines. And in order to do that, I need the theory of open quantum systems. I'm going to go through it maybe a little bit fast, but we need this background. And the main idea is what's called a reduced description. We assume that the whole universe is quantum, and this dynamics is generated by a Hamiltonian, a global Hamiltonian. And we're interested in our system, which will be our engine. And we have an environment, a bath, and we have a coupling. And if we have a separation of time scales, we assume the bath is much faster than our system. How do I go up? Then we want to get a master equation or a dynamical description of our system only, which we write it in general with this L, which is the generator of this dynamical description. And the theory of open quantum systems, there was a very important result starting from 1971, which is called a completely positive map, which is the way we want to describe the reduced description or the dynamics of the reduced description. And this theorem by Gurini, Kusakovsky, Lindblad, and Sudarshan, now called GKLS, which gives us the most general structure of the master equation. And you could say this is a mathematical construction which replaces, you can say, just the unitary dynamics, which is just given by the Hamiltonian, and adds to it a dissipative part, which implicitly describes the interaction with the bath. So this is the general partition to a unitary generation and a dissipative generation. And this is the most general form that you can write. And the assumptions are only mathematical, as I said, the reduced description. And now we want to put thermodynamics into that. And you can show, and we have shown that if you just use this form, which many people use, it can violate the laws of thermodynamics. So we have to add a restriction. And the restriction is, you can say, in a way, the first law of thermodynamics. Again, here's my partition of the system, bath, and interaction. And our restriction is that the interaction between the system and bath commutes with a total Hamiltonian, which means that energy that's lost from the system goes to the bath or the opposite, which is a way to say conservation of energy, or in another way to say it, that there's no energy accumulated on the interface between our system and bath. So you can say it's a thermodynamic idealization of a partition that doesn't accumulate energy, and we can do accounting. We have a way to do accounting. So this is a thermodynamic restriction, which gives us the first law of thermodynamics. What's lost from the system goes to the bath. But mathematically, this restriction tells us something that is very useful, that the map that we're going to describe our system commutes with the free map of the system without the bath, which you could say is a mathematical property, which will become very useful in the next slide. So the free dynamics is described like that, and it commutes with this map. In addition, we can show that this restriction leads to an equilibrium state of our system, and it's an equilibrium with a bath temperature. And you can say the second law comes from the property that there is a monotonic approach to thermal equilibrium. So we see that by adding what looks like a mathematical construction, we built a quantum theory that's consistent with thermodynamics. So now, what does it mean? It means that we can get the master equation explicitly, and we know what each term in the master equation is. And also, it imposes detailed balance. That means that our fixed point of our map is a Gibbs state. So it means we reach thermal equilibrium. So you can say the properties are that we can identify in this construction what these operators F are, and there are common operators with the free propagator. So in a way, this gives us a lot of power to get a master equation that's consistent with thermodynamics. And we can say that what we get out of it, that the unitary part commutes with the dissipative part. So this has another strong implication, which you can say all come from thermodynamic considerations. Now, once we have this construction, or the GKLS equation, we can go to Heisenberg form and write it like that. And then we want to see how the first law of thermodynamics looks like. And what we do, we insert as the operator X, the Hamiltonian itself. And we get that the change of energy splits into two parts, one that we can interpret as power, and the other one as heat flow. So now we can get in our theory a direct connection to things that we can measure or we can associate with quantum engines. And this result has been obtained by Robert Alitsky, which his picture is here, but also by Spon and Leibovich about the same period, 1979, 1978. So now we have a theory. And once we have a theory, we can deal with the same, you can say, model that we saw before, let's say this 3-level laser, with tools that come from quantum mechanics, but we have now dynamics, not only static considerations. And the first type of engine that I want to describe are continuous, which are equivalent to turbines, which I have here on the left. So what the point I want to show here, that you can say this 3-level amplifier is in a certain sense equivalent to a jet engine. And let's analyze it, but I want to analyze it using a special type of refrigerator. And we know that engines and refrigerators are just the same thing, or operate the same construction, with just the questions in which direction we operate. And the absorption refrigerator is a refrigerator that uses heat to cool. So now we're in winter, we don't care about it, we use heat to heat. But if we were in the summer and we have a large hospital and we need to air condition it, and we want to be sure that even if there is a power cutoff, we'll have cooling power for our refrigerator, we would use an absorption refrigerator, and the source of, you can say, power for the refrigerator would be diesel fuel or whatever. Now, this refrigerator has a patent by Leo Szilard, and together with Einstein, which we already heard about, and they were good friends, and they were at the Fritz Haber Institute in Berlin. Szilard was a student, and Einstein had his office there at the Institute. And they became friends, and then they read in the papers that there are accidents in refrigerators in Berlin at the time, in the 1930s. And the reason was the refrigerators worked with ammonia, and ammonia is poisonous, and then when there was a leak, people would die from that. So they said they should do something practical, and they invented this absorption refrigerator, which has no moving parts and doesn't have any ammonia to operate it, and it works on heat. And they patented it. And Einstein thought that Szilard needs the money, so he gave all the rights of the patent to Szilard. He thought that Szilard is a poor student. What Einstein didn't know, that Szilard was from a very rich family and he didn't need the money at all. But eventually, they both left Germany and nobody gained from this patent anything. So it's not so bad. So the main idea here is to use heat to cool. I'll show you how it works in the quantum state. It's much easier to analyze the quantum absorption refrigerator than the, you can say, the classical one here, which is the invention. And so let's see how it works. And the question that I want to answer using this absorption refrigerator is how small a refrigerator can be. And in a way, you could say when we think about thermodynamics, we think about steam engines, you can say power plants, big things. And thermodynamics looks to most people as a kind of macroscopic theory. And the question is, how far can we miniaturize it? And what I'll try to convince you that there's no lower limit. You could define a quantum device out of nothing, or not nothing, but 2, 3 levels is sufficient. So thermodynamics is not limited by the scale. So the absorption refrigerator, you could say, is an example of that. So let's see how it works. So here I have, in this case, 3 baths. I want to cool the cold bath. I have a source of heat, which I call TW, and I have a hot bath. So how does this work? If I have heat at the hot bath, naturally it will go from TW to TH, because this temperature is the highest in this device. So heat will flow from here to here. So this is a natural flow of heat. But now if I can enslave this natural heat flow with heat coming out of the cold bath, then if heat will move from here to here, on the way it will pick up heat from the cold bath, and I'll get a refrigerator that's running by heat. Now, in quantum mechanics, we can describe it by a very simple Hamiltonian. Let's say I have 3 oscillators or 3 2-level systems, it doesn't matter. One was frequency omega h, the hot one, omega c, the cold one, and omega d, this power. And now my interaction, look how it works. It takes a quant from my, you can say, my heat source, D. It eliminates a quant from here. It eliminates a quant from the cold bath and generates a quant in the hot bath. And you can say this is the conjugate. So this piece here works as a refrigerator. It takes a quant from here, a quant from here, combines it, and makes one quant here. So automatically we see this is a nonlinear device. And this is one of the theorems that you can say about systems, that a refrigerator or an engine has to be a nonlinear device. A linear device can't work at all. And so this is the part that you can say the crucial part of our refrigerator. And now you can do an energy balance. You can say the sum of all current at this point should be 0. So this is conservation of current, or of energy if you want, if these are energy currents. And from the point of view of entropy, we can say that the total entropy generation of the whole device has to be positive. This is the second law of thermodynamics. And this inequality should work. So if you could say the heat source is hot enough, we can basically eliminate this part, and then we can get this condition for this device to operate. So we can say that we'll see that eventually this condition translates to something that's very close to the auto efficiency, which comes out from this inequality. So this is the device, an absorption refrigerator in quantum mechanics. Now let's see how it works. But first I'll reverse it and look at it as an engine. And I'm doing here a simple trick. I'm replacing this hot source by a C number. This is a semi-classical approximation. So this would be a driven refrigerator. I have a power source, a zero entropy source, which is a power source, and I pump energy from the cold bath to the hot bath. This is how our refrigerator at home works like. So I replaced, you could say, what we had before by a C number, by this frequency driving with a certain frequency nu. And once you do that, you can see that the efficiency of this device is the auto efficiency, which comes from that the entropy production is positive, and we can get the energy balance like that. So this device as a refrigerator, you can analyze, you can solve it because it's completely linear now. And you can reverse it and make it an engine. You can say, no, I'm taking my heat and flowing from the hot bath to the cold bath and getting power out. And you can see that the power is this frequency times the coupling times the gain, which is the population difference as we had before in the 3-level amplifier. So the power will look like that. And if you look at the efficiency at maximum power, you get this expression, the Coulson-Alboron efficiency at maximum power, 1 minus the square root of TC divided by TH. So now I hope I showed you the close relation between a refrigerator and an engine. Now let's take this model even further. Here we can look at again as an engine, and to see this trade-off, this is the power. You can see it's the gain times the coupling to the environment, the frequency, and this is its width. We can optimize it further and we can get this expression that I showed you before. It's proportion to the gain and the frequency. And what you could say, I can take this graph and write the efficiency divided by the Carnot efficiency and the power divided by the maximum power. And we get this very nice plot which shows you the trade-off. You could say this point here is the maximum power. And here I can read the efficiency at maximum power, which you can say is only 60% in this case from the Carnot efficiency, which here is 1. So this is the maximum power. This is the maximum efficiency in this device. And what you see, it goes to 0 here. A turbine has to turn. It never can reach the Carnot efficiency because there's always a heat leak. So that's why this graph closes on itself. And you get this kind of universal trade-off between power and efficiency. And just tells you that the turbine, you can't work on it too slowly because there's always some friction and some heat leak. And this is just to show that there is always a maximum in power. Here is the coupling to the radiation field, epsilon, and this is a coupling to the bath. And you can see there's a maximum of power at this point here, which is a universal property of all, I would say, all heat engines. So now let's go back to a refrigerator. We can operate this refrigerator by noise. A power source can be pure noise. It's funny to think like that, but the pure noise it's a zero entropy source. Took me time to think about it a little bit. But you can drive the refrigerator by pure noise. I still can pump in this direction. And then we can analyze this refrigerator and ask, okay, how cold can it reach? And this brings us to the third law of thermodynamics. Here's Nernst, the big mustache. And when we analyze this device, we can see that the cooling power that we get out of that has three parts. Has a quant of energy that I'm taking out, h bar omega c, which is the, you can say, the part that's coupled to the cold bath. I have a kinetic term, which we call the coupling, and I have the gain, which is the difference in population between the cold side and the hot side. And for a refrigerator, NC is always larger than NH. Now, if we want to see what happens at low temperatures, we can look at the scaling of this, these terms here. And we find out that, first of all, that the frequency that's connected to the cold bath has to be proportional to the cold bath temperature. The kinetic coefficient has a certain scaling that depends on the model that we describe. And the gain, if we optimize, becomes a constant. And out of that, we can get the third law of thermodynamics, which tells us that we can approach absolute zero, but we can never reach there. And the question is, if you want to quantify it, what is this exponent on this TC? And we know that this exponent has to be larger than 1. Otherwise, we can reach absolute zero in finite time. Now, this third law is, you could say, very relevant today, because if we think about a quantum computer, we need to have cold conditions, and people call about a cold ancilla qubit. But what this tells you that you can never reach there, you can get close to it, and this would be the scaling that you can get to if you want to get a cold ancilla, or you want the whole computer to be cold. And the entropy production has another scaling, alpha, which has to be larger than 0, because entropy production, again, the second law of thermodynamics tells us it has to be larger than 0. And the third law takes this equality here and says it's a strict inequality. And we can analyze it for a cold Bose or Fermi gas or harmonic bath or radiation bath. And we can get explicitly terms for these exponents. And the next graph would just show us this shows us the cooling current as a function of temperature. And we can see it goes to 0 when the temperature becomes low with different exponents. You can see phonones, Bose gas or Fermi gas. And we can look at the entropy production and the graph below, and we can get the scaling. So in order to get this, we need a dynamical model, because only a dynamical model can tell us how fast can we reach the absolute zero. What Nernst told us that it would take infinitely many steps, but you don't know how long will that take. This puts a restriction on the exponent, which gives you a, you can say, quantifies the third law of thermodynamics. Okay, now what I described would look very abstract, but the nice thing about the field of quantum thermodynamics, that smart experimentalists decided that if you can write a Hamiltonian, they can build it in their lab. And this group in Singapore of Maselnikov decided to build this absorption refrigerator here, exactly this tricycle, this 3 coupling, nonlinear coupling. They built it out of an ion traps, and using 3 modes of 3 ions in a trap. So you can say quite a small device. You have 3 ions, 3 oscillators coupled to each other non-linearly, and that's sufficient to realize in the lab an absorption refrigerator. So you can say this model has been constructed. It's not only abstract. So now let's continue to what's more maybe familiar is reciprocating heat engines. And what I'm showing you here to the left is, I think, taken from a museum in Britain. It's a very early version of an Otto engine. So it's a cylinder and you say have gas and you have whatever and it's turning around. So you can say it converts heat into automotive power. And we can ask again the question, how small can it be? What's the role of quantum coherence in this engine? And can we use ideas of coherent control, which is controlling interference to optimize our engine? Is there something quantum here? And if you look at that, it doesn't look very quantum, but if you look at recent papers on quantum devices, which are becoming quite popular about, and here is a paper, you can see thermodynamic analysis of quantum error correction engines. So the idea behind it is that the reciprocating engine works by a series of operations, which is very similar to what you do in a quantum computer. Quantum computer can be described by a sequence of unitary operations, one after the other. And in a way, you can think about this as an engine. It has the same properties of an engine. And what I show you here below is a Josephson junction, you can say element. Here's a 2-qubit element of a quantum computer, which people have shown that you can make an engine out of it. So let's see how this works. How can we build a quantum, let's say, Otto engine or Carnot engine and analyze it? So here's the idea. I need, again, a propagator, which takes our state from state I to state F. And if I want to describe a 4-stroke engine, I need to concatenate 4 strokes from the hot to cold, a cold one, a cold to hot, and a hot one. And this, on the left, it's a Carnot engine. On the right, it's an Otto engine. And altogether, my propagator of the cycle is a product of 4 operations. You can say it's cold to hot, then equilibrating with a cold bath, hot to cold, and then equilibrating with a hot bath. And what's interesting, if you want to think about this in quantum mechanics, that these propagators can't commute. If they commute, the order wouldn't matter. So we know in engines that the timing is very important. So try to change in your car the timing of the operations and the engine will explode. So you can say even our car engine knows about the sequence of things that happen, and which means that these operations cannot commute with each other. And so this is a question, how is our car quantum? I can give an answer to that later if you're interested. So here is an idea of a Carnot cycle working on a single spin. So I can look at the polarization of my spin as a function of, you can see the frequency. So I put a single spin in a magnetic field. I can change its energy level difference. So omega is the, you can see the Rabi frequency. And if I can change my energy differences, I can run either a Carnot engine, which is, it has 2 isotherms. You can say, I'm running here while I'm connecting to the hot bath. I'm going here from hot to cold. This would be called the thermodynamic adiabat. I'm on the cold bath, and you can say an isotherm, constant temperature. and I close my cycle. So this cycle would be a Carnot cycle. And embedded inside, I would have an Otto cycle, which you can say is a rectangle in this kind of graph. So I equilibrate, I do a small adiabat, I equilibrate again, and I close. So you can see this area is what would be the work. And you can say the efficiency for this Otto engine would be this area divided by this larger blue rectangle. The Carnot, you can say, would be this green divided by the same area. This is the heat that I'm dissipating to the cold bath. So you could say that the Carnot engine is more efficient than the Otto engine. This is not surprising. Now, for qubit, we know the polarization. If we have the temperature, we can calculate that. So this would be a model of a single qubit engine. We can compare this to the Otto engine to a Carnot engine in another way. What I'll show you later that in the Otto engine, the efficiency at maximum power again becomes the same Coulson-Ahlborn value. Okay, so what do we want to learn about these quantum engines? We know that in real life, heat engines operate at finite power. They're limited by heat leaks, and the motion is subject to friction. This is all universal. All engines work like that. Here we have August Otto, the inventor of the Otto engine. And this is related to a field that's called finite time thermodynamics, which you could say this paper by Bian Andres and Peter Solomon and Steve Berry just passed away recently. They looked at it from a phenomenological point of view. They wanted to put these characters of an engine into the theory. And what we're doing, we're basing it on a quantum mechanical first principle ideas. So you could say, do quantum engines work at the same way as these classical engines? And I'll show you that the answer is, in most cases, yes. So here's an engine, a model of an engine working with a working substance is just a harmonic oscillator. And it's an Otto engine in this case. You can say I can start from this point. Here's my oscillator. Here are the discrete energy levels, so it's quantum. I equilibrate it with the hot bath. So here's the population. You can say here's in the ground state, the next state in here. I change frequency. That's where I get power. So I change frequency and keep the populations the same. So I get work out of it, which would be the change in frequency times the population. So this is the amount of work I get out of it. Then I cool it. So I put population in the ground state, I get less. And then I do a compression. So I also need work to do that, but I'm colder. So the population is lower. So altogether, I get more power in this direction that I need in the compression. So you can say the total work that I get out of this Otto engine is delta omega delta n. The change in population times the change in frequency times h bar. So what I showed you here, I constructed an Otto engine out of a working medium, which is a harmonic oscillator. The same I could do with a single spin. It looks very similar, but there is a certain point here which is quantum mechanical. Here's my Hamiltonian. It has kinetic energy plus potential energy. And what I'm doing in this step, I'm changing the potential energy. I'm changing omega of t, which is my potential. But if I look at this, they don't commute. The kinetic energy and the potential energy doesn't commute. So it means that my description here, from here to here, is adiabatic. That if I want to do things fast, the kinetic energy doesn't commute with the potential energy, I'm going to pay for it. And this price is generating coherence. So this is the quantum mechanical price of working beyond the adiabatic limit. But if I would think about it from the point of view of the engine, it's friction. In order to generate coherence, it costs me work. So if it costs me work to do something fast, I can think about it as friction, and phenomenologically, it behaves exactly like friction. And the source of it, that the Hamiltonian doesn't commute with itself at different time, or it's a quantum mechanical source that, you can say in this case, kinetic energy doesn't commute with potential energy. And this is the important statement that people have worked on this quite a lot, and this is very definite, that coherence costs work. We can bound that, and we can get an understanding. What does it cost to run our engine fast? And there is a way to analyze it, and using a set of quantum variables. And let's go on. I want to show this picture. We can think about a harmonic oscillator in phase space, which is position and momentum. And here's how my energy shell would look like. So in position, this would be a parabola of the potential, and momentum is always p squared, so it's also a parabola. And this would be the state that I think my quantum state is inside. So if I equilibrated it, it would look like that. It's spread in this way. And if I move from here to here, I change if I do this very fast, let's say change my potential very fast, this would be a sudden move. You can say I'm generating a squeezed state. My quantum state is not in equilibrium with its, you can say, its potential and kinetic energy. And a squeezed state is equivalent to generating coherence. If I equilibrate it, you can say I get it round again. If I go here, I get a squeeze state. And these moves, which I try to do things fast, would cost me. So again, there's recent work, here's work from 2000, already 5 years old, that this engine has been realized with a single ion trap. So you can see here's the single ion in the trap. The whole idea of the trap, that it has a shape like that. So if I move in this direction, you can say move from a high frequency to lower frequency. This is what we need to realize our auto engine. Now, here's what they show in their graph. The difference is I couldn't control their paper. They go in the opposite direction that I go. So here's the hot side, and here's the cold side to the right. And they, you can say they generated a single ion engine, a single ion in a trap. So you can say there's no real limit how small a quantum engine can be. More recent work from the same group has changed this construction, made the engine, instead of the working medium from a harmonic oscillator, it made it from a spin, also the same ion here. And they coupled it through, you can say, basic quantum operations. What they really did is they took a model of a quantum computer and made out of it a heat engine, which a single ion heat engine, and the working medium was a single spin. So there's no limit how small we can make a quantum engine. Now, there's a lot of optimizations you could go. The first one is called shortcut to adiabaticity. And And the idea is that since coherence generation requires work, if we have coherence and we know how to define it, we can convert coherence back to work if these operations are reversible. And they are, provided this is a unitary move. So if it's a unitary move, we can generate coherence and we can cache on it. We can use it later. And this is an idea which goes under the name shortcut to adiabaticity, which means that intermediate times we can generate coherence. What's important is when we're in contact with a hot or cold bath, no coherence is left. So we don't dissipate coherence and then we have a loss. So this is one idea. And the other idea, and this is when we started to think about the Carnot engine, that while we drive our engine, it's in contact with the bath, so it becomes a more difficult problem. So we need a dynamical description for a driven system coupled to a bath, and we have to go beyond the adiabatic limit. So the theory that I showed you before of the master equation doesn't apply in this case. So we had to develop a new type of theory for driven systems, which is consistent with thermodynamics. So we set to do that. And that defines in a way a control problem. I want to go from state I to state F. I can change my Hamiltonian, but I have no control of the bath or the system bath coupling. And to do that, I need to obtain the correct master equation, which is consistent with thermodynamics. So we had to develop this theory. Once you do that, that's fun. So maybe we were forced to do that, but we were quite happy to do that. So we derived a master equation which complies with a driven quantum system. And don't want to go into details. And then we can deal with the isothermal dynamics in a Carnot type engine. And what we get in a situation like that, in a unitary evolution, the entropy is constant of motion. When you're coupled to the bath, the entropy can change. So it allows you much more freedom. You can do more types of things when you have a bath than you don't have a bath. It means the controllability of the system coupled to the environment increases, which is an important subject. Here we try to speed up equilibrium. So we wanted to find a protocol that we can go faster than just, let's say, let's change our frequency and just wait for a new type of equilibrium. And so you can think about it as a, let's say, harmonic oscillator or a two-level system, whatever, that I start at a high frequency, I go to lower frequency, and I want to equilibrate with the temperature of the bath as fast as possible. And what we found out that if we overshoot, it's always better. We can always get a much better protocol. And it means that we generate a lot of coherence on the way. And that's why our coupling to the bath is faster. And eventually we cache on this coherence and become to a thermal state which has no coherence. So this works in both directions. And we found these new types of protocols, which are quite interesting. So these shortcuts cost you. So adiabatic shortcuts, you could say, cache on the coherence, and you can say the total entropy change is 0. So you can say, you can classify adiabatic shortcuts as a catalysis type of thing. You store in the middle energy, but then you use it. But if you look shortcuts to equilibrium, it would cost you entropy. So the amount of entropy that you generate in the universe is larger than 0. So the speed up cost entropy and extra work to make the engine go faster. And we'll see that in a minute. So this brings us to a general theory of quantum control of open systems. We can think about controllability and constructive mechanism and optimal control. So that opened the door for us for a new subject of study. And just to show you of a control task of going from one equilibrium state to another, this is what we're doing here. But what surprised us that if I'm thinking about my bath, I can reach in a final state colder than the bath temperature. So what do you have here? For example, I have a system. It's in equilibrium with the bath and I drive it. And if I do it in a clever way, I can reach a final state that's colder than the bath temperature. And there's nothing wrong with it. This obeys the laws of thermodynamics. Basically, it works like a refrigerator. Since I put power in it, I can dissipate in such a way that eventually I can reach a colder temperature than the bath temperature is. This is a transient state. If I wait, eventually it will reach no equilibrium. These are these protocols that lead it for a spin. We can increase purity or we can decrease purity. This is what I said, that we can change entropy of our system. It's not a unitary move. And finally, we can use these ideas to build a model of a Carnot engine, a four-stroke Carnot engine that works at finite power. And what I want to show you here, again, this is the same graph I showed you before, the trade-off between efficiency and power. So here, this is the point of maximum power, and this would be the efficiency at maximum power. Here we get 60% about. And we can get very strange looking cycles. And if we look here, for example, at the efficiency divided by Carnot efficiency as a function of cycle time, if I make my cycle shorter, eventually friction is going to take over, and you can see at a certain cycle time, friction is so large that I get nothing. My engine stops to work, and I basically put power and dissipate everything to the bath. But we found what we call a global cycle, which has global coherence. We never imposed that it would be without coherence in the cycle. And to look at that, here, this is a cycle that never touches equilibrium. It has global coherence. And here, this is coherence through the whole cycle. I never reach a state that I have no coherence in the cycle. And this cycle can reach, you can say, 0 cycle time. And we have shown before that a four-stroke engine, which I describe now, in this case, a Carnot engine, which is described as a product of propagators in the quantum regime, where the action is small, and action is measured by the h bar. When the action is small, you can take a product of exponentials of operators and make a sum out of them. So you could say that a four-stroke engine is equivalent to a turbine, an engine which I started before. So we have an equivalence theorem between a four-stroke or an n-stroke engine, doesn't matter really, and a continuous engine in the quantum limit, where the action is small. So this is this figure here. You can say that a two-stroke engine on this scooter, or a four-stroke engine on this car, and a jet engine, all in the quantum limit become equivalent in a certain case, and which looks a little bit maybe strange, but you could ask, okay, what really defines this as a quantum device? Why can I say it means it has coherence? And you need a good definition. What do you mean that this engine has some quantum features? So the simplest thing to think about it is this definition that a quantum device, if you look at it, it doesn't work. And this definition is also good for a quantum computer. And it's also good for me in my office. If my students bother me, I stop to work. And it's the same in a quantum computer or a quantum engine. You have to allow it to do what it wants. And then when it finishes, you check what happened. And if you bother it on the way, you get nothing. So this is the definition. You can try to check our model, and the way to do it, you use a theory of quantum measurement, you measure it and you see you lost all power. So this is a way to check that your engine is really quantum. And another point is that the energy scale changed from kT to h bar omega. So we talk about the quantum energy and not continuous energy, or the unit of energy changes. And you could say we can find frictionless quantum protocols for the unitary part, which we call shortcuts to adiabaticity. And then we showed that in the sudden limit, where the action is small, we can get a quantum engine that coherence is essential. And this is the equivalent region. Now, this has been realized recently. Here's a paper from 2019. The experiment was done using ENVI Center in Oxford. And what they did, they compared a continuous engine working on, you could say, in a qubit as an operating medium with a two-stroke version. That's what they could do. And the way to show that this is quantum, here you can say the point they're reached here. This is, you can say, a theoretical limit. If you pass this limit, you know that the only way that this engine can operate in this region if it has a coherence. And here, experimentally, they were satisfied with 4 sigma. You can say the distance between here and here to really prove that this engine is really a quantum version of a, you can say, a two-stroke engine, which becomes equivalent to a turbine or a continuous engine. Okay, so maybe I talked too much, but that you gave me the opportunity, so I couldn't stop. And since you can't shout at me, you can shout, I won't hear in Jerusalem. Here's our conclusion. It was a long voyage. I hope I could take a boat and come to Mirsin. And we were looking for a quantum open system description of a Carnot cycle in a way that I started to look at that maybe more than 30 years ago, maybe almost 40 years. And it took a long time, but the journey is fun. So we got many results. We got non-adiabatic master equation. We got a new theorem on which we call the inertial theorem, which allows us to analyze non-adiabatic dynamics. I didn't talk about it. We looked at shortcuts and entropy changes, which is quantum control. And eventually we found a finite time quantum Carnot cycle. And here I just talk about the quantum signature. So all these things that all came out, you could say, by trying to, you could say, understand consistency between thermodynamics and quantum mechanics on the most simple case of the Carnot cycle. So maybe it took many years, but it was fun on the way. And the main thing is what we learned on the way. And for here, I thank you for staying with me.
Toda raba, Ronnie. Toda raba. Thank you very much. Let us thank Ronnie by unmuting our mics and clapping our hands if possible. Thank you, Ronnie.
Thank you.
So now the question, I mean, are you tired, Ronnie, or?
No, I'm in good shape.
Okay, I know you are never tired, so. So any questions? Let me see. Serhat Kadıoğlu, please.
Hi. I have a question. There are many discussions in the efficiency of the quantum engines. So some people suggest that there is very small efficiency, and some of them claim you can do some work with this. So some people are very pessimistic, like there is one paper, Vanishing Efficiency of a Speed Up Ion in Paul Trap Otto Engine. This is a paper of A. Tobalina and J. G. Muga. So they claim that the efficiency of the engine is very small, like 10 to the minus 7, something like that. So
Okay.
what is your idea on this whole cost or I'm asking that some people claim that this is not feasible. You cannot obtain any meaningful work from these engines. What is your take on this cost problem?
Yeah, okay. So I know the paper, and I know both Muga Gonzalez and Ander Tobolina. Yesterday he got his PhD. One of the authors there, he would defend his PhD yesterday. So the issue is, okay, when you start to account, the question is what do you put in your, what do you account? So you could say the original analysis looked at the quantum part of the engine and said, okay, what's the output? And if you look at just at that part, you could get, okay, don't think they were interested in very high efficiency, but their efficiency was, I don't know, 20, 30%, something like that. But if you want to go beyond that and include the controller, because this is a quantum system and it's controlled. So if you want to take the controller into consideration, then the efficiency becomes very small because the controller is classical and very large. And what your engine is just this single ion in this ion trap. And you can say most of the power is consumed by the controller. So this is very an unbalanced situation. And I would say this is not surprising because this is more a demonstration of what you can do than to try to make an efficient engine. But I would say the point, if you think about where do you want to use a quantum engine and technology, it's a technological question. It's not so much a scientific question, directly a scientific question. It's more technological. And what I like to claim that what you want now is a refrigerator. And if you want a quantum computer, so what do we know about quantum computers? They work at temperatures of, I don't know, 10 to the minus 3 or 10 to the minus 5 Kelvin. They sometimes even colder. So a quantum computer needs a refrigerator. And if you, when I was in Santa Barbara, I went and visited the Google computer to look how it looks. I was curious. And what do we know about the Google computer? That the actual size of the computer is about 1 centimeter by 1 centimeter. This is the chip that these qubits are sitting on. So it's a Josephson junction based computer, and it's quite small. But what is the size of the refrigerator? It's about a very large barrel. It would fit into my office. I would say it's 1.5 meters on 1 meter. So the refrigerator that they used is huge and the device is quite small. Now, when you see that, you understand that as a demonstration, it's okay. But if we want to think that a quantum device will be effective or useful, part of the device is a refrigerator. We have to cool the quantum part in order for it to operate. So what we really need is a quantum refrigerator. And so we need the reverse engine. And there's, I would say, encouraging work in Finland. And they show that the efficiency can't be high because the Carnot efficiency is very small if there's a big temperature gap. If I want to cool to 10⁻³ from room temperature, you immediately see that what's called the COP, which is the inverse of the Carnot efficiency, is very bad because I need to put a lot of power to get rid of this gap. But this is thermodynamics. And then you ask, okay, how much I pay for finite power? You pay, but I would say it's reasonable. So refrigerators based on a Josephson junction device are even today quite reasonable. And what I envision that if you have a quantum computer based on Josephson junctions, part of it, you could say, let's say you want 50 qubits to do your computation and another 50 qubits to cool it down. And then hopefully the device wouldn't look like a huge barrel and a small device inside, but it would look like, let's say, your laptop computer, something like much more reasonable as a device that does work for you. So I hope I answered partially your question.
Thank you very much. So Ricardo, Ricardo has a question. Ricardo, I don't know if he is still online or yeah, he's here. He doesn't have a microphone. So Ronnie, let me read it. Ricardo doesn't have a microphone, but his question is the following. Can you comment a little bit on why a source of pure noise is a source of no entropy?
This is a little bit subtle. So you can think about, let's say, the opposite. I have a tricycle. 3 sources are a hot bath, a cold bath, and a heat bath. My source, and I can run it as a refrigerator. But I can run it in the other way around. I can take heat from the hot bath, dissipate it in the cold bath, and pump extra heat into the, you can say, my source, my temperature source. Now, what's the entropy of the temperature source? It's the amount of heat that I got divided by temperature. So if the temperature becomes infinite, the source has no entropy generation in it. So what is pure noise? It's equivalent, you can think about it, to infinite temperature. So infinite temperature is a source that doesn't carry with it entropy. I can take out of it heat, and it doesn't cost entropy because the entropy is the amount of energy I take out divided by temperature. So this is, you could say, the justification of thinking as pure noise, which is equivalent to infinite temperature to a 0 entropy source. It was a good lesson because it tells you that you don't need really in a semi-classical description or a driven system, you think about zero entropy source is pure work. So if I have a coherent generation or power, it's also a zero entropy source. So there's an interesting equivalence, you can say, between pure power and infinite temperature.
Thank you very much, Ronnie. Any other questions? Any other questions?
I have a question.
Question.
Dear Ronnie, thank you very much. This nice talk. I have two questions, and the first one is related with the inserting dynamics into thermodynamics. You know that sometimes coupling to the environment can also contribute to the unitary dynamics. And if we are not able to drive our master equation microscopically, then we can not uniquely decompose the unitary effect and the dissipative effect of the environment. In this case, is it possible to identify heat current properly? Do you know, is there any proper way to identify the heat current in this case? If we are not able to drive a microscopic master equation, can we do something more?
Okay, so I think I understand what you want. You can say there are traditionally two approaches to the master equation. One is a microscopic derivation. And this relies on a series of assumptions, which is, and you can say there are many approaches to that. And which is not always so easy. If you take a specific system, you have to do many approximations. You don't know if they're correct or not. But I would say in the standard derivation, which I call Davis, the weak coupling limit and what's called Davis construction, there are two main assumptions. One is a Markovian assumption, a separation of time scale. And the other one is called the secular approximation, which eventually you need that to get the form of the master equation, which is a GKLS master equation. So this is microscopic derivation. And then you would ask, is this consistent with thermodynamics? And the answer is yes. The Davis construction is consistent with thermodynamics, but it's global. And many people take, they don't use a secular approximation or they use a local approach, and you can show that this can violate either the second law or the third law of thermodynamics. So this bothered us and then we said, okay, let's try to go around this problem and impose thermodynamics from the beginning. This is what I showed you. All what you need to do is add strict energy conservation before you derive the master equation. And you don't have to do an explicit microscopic derivation. That's all what you need to do, and you get a consistent equation. It has a similar approaches going to what's called the resource theory or thermodynamic resource theory that was done by Horodetsky and Oppenheim. They also put in a different way through a unitary operator strict energy conservation, but they didn't do a dynamical theory. But we use it as a dynamical theory. That's very useful because if we look at the secular approximation or the Davis construction, we can identify the property that we expect, which means that the unitary part commutes with the dissipative part. So you could say thermodynamics imposes that the unitary part, so once this happens, then it's easier to identify heat and work. This is, you can say, I would say part of work that is in progress. Now we're trying to write a paper that will be consistent and try to put these definitions under these assumptions, but we haven't finished this work. So this is really work things that we're working on now. But I would say for many years we went through the microscopic derivation until we understood that we want to go around it.
I am impatient about this paper as well. Thank you very much for your answer. And I have one more question if you have time.
Yeah.
This question is about the role of quantum coherence and correlations. For example, consider the absorption refrigerator. In this setup, we can also consider some non-thermal heat beds, such as these heat beds consist of particles. Each local state of the particle may be a Gibbs state. Then it means that there is a local temperature for each particle. But these particles can share some quantum coherence and correlations initially. And in the process, this coherence can be consumed.
This correlation?
Yes. Instead of, you also mentioned about generation of coherence, but this time consider the reverse happens. The initial coherence in the heat beds are consumed during the process. I think there is a possible interpretation such that instead of the local temperature of the particles, we can say that they have an effective temperature, which also includes the effect of the shared coherence or correlations. But can we, instead of this interpretation, can we say something, can we, how can I say that? Barış hocam, anlam yüklemek nasıl derim?
To give a meaning to it.
Can we give a further meaning to quantum coherence and correlations in such a setup? Because as far as I know, in the research theory of thermodynamics of Horodetzky and Oppenheim, I think they give further meaning to quantum coherence and correlations, and they are trying to generalize the second law in the sense that, for example, they use thermomajorization criteria instead of traditional second law. Here, can we expect similar things in your point of view?
And Ronnie, by the way, I would also like to ask something in this context, so let me ask. Like, you go with the usual second law, but for example, Oppenheim and Brandao and these guys in resource theory, what they do is something called majorization.
Yeah.
I would really wonder your opinion now, because when I was in Israel with you, I didn't study these things, but now I know. So those two things, resource theory and your way, I mean, the idea, the main idea, like quantum thermodynamics as an idea, it's common. But the way you eat it, let us say, or you digest it, is totally different. For example, there is no time there. And second law is in terms of something called thermomajorization. But in your case, there is time, and also you just look at it, the second law in the usual way. I would really like your expert opinion on this. I mean, if you can.
Yeah, okay, so I would say the main point is, the main difference is time. That you could say the resource theory came from, you can say, computer science originally, when they think about a series of operations. So you say I do, and their operations, their primitive operations are typically unitary operations. Now, if you use a unitary operation, what you can do is limited, because if I take a unitary operation, I can't change the eigenvalues of my density operator. They're a constant of motion. So what I can do permutations. I can change the order, but I can't change the eigenvalues. So what they ask under unitary, you could say one way to think about resource theory, which states can you reach thermodynamically under unitary operations? So it's limited, and you can say there are generalized second laws. You can say using Renyi entropies is what is called single shot. They try to allude to what they would call single shot experiment, that you take your system, you're allowed to apply a unitary transformation, and you ask where can you reach? And they elaborate by making their system more complicated, adding what they call a catalysis and things like that. And so if you add a catalysis and you allow it to change epsilon, you can reach more states. So eventually you throw away the catalysis and you can reach more states that you can only reach by a unitary operation. But I think what I showed is once I add a bath and I allow myself to interact, I can act anywhere because I can change entropy. And I can change entropy in both ways. So let's say I have a bath with a certain temperature T. So I can, and I have just a qubit, so I can go to very high frequencies, so I'll reach the ground state, or I can go to very low frequencies and I'll equilibrate the two levels. So you can say that I have a lot of control. If I couple to the bath, I can really change entropy. So the accessible states, the set of accessible states is much larger if I'm allowing myself dynamically to contact the bath. So in a certain sense, I think what they're doing is okay, but it's restricted. You can have more freedom if you dynamically allow yourself to, because if you think what they allow in their set of rules is only to equilibrate.
Yeah.
But I don't want to equilibrate. I want to be in contact. You can see part of the way it works. You could say, how can I speed up equilibration? So if I equilibrate, typically you say, okay, jump into the bath and I drink my beer until I equilibrate with the bath. This is one way. So this would be sudden. And that takes time because it goes as a heat conductivity. And the reason it takes time, when I get closer to the temperature of the bath, it's just the process becomes slower and slower. So that's why to reach equilibration takes a long time, because it goes as a difference in temperatures between me and the bath. So how do I overcome that? If I want to speed up the equilibration, I want to stay far from equilibrium as much as possible. So the way to do it, I generate coherence. So already I'm out of equilibrium because I have coherence. So I generate coherence. I'm far from equilibrium. I'm coupled to the bath. I have a fast process. And at the right moment, I rotate back. I change this coherence back to energy. So I get rid of it. And that's how I can speed up my equilibration.
Okay.
So,
Time is the keyword here.
Yeah.
Shall I ask one more thing about this, Ronnie? Because I remember a paper of Nicole Younger about photoisomerization. In this paper, they look at the dynamics and also they look at the thermomerization criteria. And I think their claim was that this thermomerization is also valid for non-equilibrium case, because the maximum yield of the process found by the thermomerization is obtained before reaching the steady state. in their calculations. They solve the master equation, look at the dynamics, the yield increase at intermediate times, and then decrease a particular value in the steady state. And this maximum actually is the same with the one that they found from the thermomeasurization.
Okay, I don't know this paper, but it sounds interesting. Yeah, I don't know this work, but what you're describing looks to be correct. If let's say I showed this example when I can create a state that's colder than the bath. It's transient. If I wait, it will equilibrate. So this is reasonable. If I stop my process there, I reach the final state. My target was a very high fidelity, but I did it in much faster, and I got a non-equilibrium final state. It's consistent with thermodynamics because in order to reach there, I had to dissipate a lot of heat on the way. So you can do that. If you allow yourself a dynamical process, you have more freedom. This is really what is correct.
Thanks a lot.
Yeah.
And one final question maybe from Serhat Kadıoğlu.
I just wanted to ask more short question, maybe more than a scientific question. It's a student's question. I'm usually tracking of your papers, and I try to solve them like shortcut to equilibrium paper or this quantum signatures, but I had difficulties for constructing the unitary, not okay, but the constructing the propagators. So I want, so can you suggest me a study paper, like maybe one of your, is covered in one of your review papers, but I had some difficulty when I tried to calculate the those propagators by hand. At least I couldn't do it.
Oh, okay. Okay, so I suggest first you can write me and I can send you relevant papers and we can discuss. You can maybe describe more your problem. But I would say the difficulty is that in order to construct a master equation, I have to solve the free dynamics. Now, the free dynamics is not a trivial problem because I need to calculate the unitary with a time-dependent Hamiltonian. So that involves time ordering, and that's a difficult problem. So you could say once we understood that, we had to find a way to get around the time ordering. And for that, we developed a method that we call the inertial theorem, which the idea behind it is that we transform to a time-dependent operator basis using a certain unitary transformation. And there, if we figure out the correct transformation, we get, you can say, there's explicitly time-dependent construction. We get time-dependent constants of motion, which looks quite kind of strange, but these are invariants of this propagator. And out of that, we can construct a master equation. Now, it's not a general method. It's a method that we can use for certain cases. You can say for n-level systems, we can do that. There is a way to construct it. And it's not always so easy, but I think this can be expanded. we are only at the beginning of learning how to use it. We can combine two types of solutions. So if we can, let's say for 2-level systems, we solved it. So we can combine solutions of 2-level systems and make a 4-level system or 6-level system. There is flexibility in this method. So what we get out of it is a set of invariants of the time-dependent propagator, which what we need for the master equation. So there is technical difficulty here. I agree.
When I first read your inertial theorem paper, I was very happy because I tried to solve harmonic oscillator in open systems. Then I came up this problem of designing some propagator for time-dependent Hamiltonian, and I was thinking that at least I need to define a geometric phase that is acceptable for an open system. And that paper kind of agrees with my intuition. I was happy because of that.
Yeah.
So Ronnie, as far as I understand, Serhat is having difficult time in deriving some of the propagators in your paper. So maybe, is it true? Is it correct, Serhat?
Yes, hocam. Yes.
Would you help?
I would be happy to help, sure.
Okay. I will send an email to you.
Be more explicit, and we can we can send you, you could say notebooks of the Mathematica or whatever the derivations. We have everything.
Serhat, açıkça hocaya yazarak sor canım. Tamam mı?
Tamam.
Okay. I believe that there are no other questions because I don't want to be punished by Ronnie's wife. Any questions?
Thank you for the answer again.
Yes, we all thank you for the beautiful talk and these series of answers to our questions. Thank you very much, Ronnie.
Yeah.
I really thank you for having time. And hopefully very soon we will be in Mersin together.
Yeah.
But I can tell you that yayın in your house is better than here. So I talk in a strange language. So thank you very much again. And we always welcome you here in Mersin University and in Turkey in general. Thank you very much for sharing your knowledge with us. And thank you to everybody for participation.
Yeah.
Thank you. Netraut. Bye bye. Herkese iyi akşamlar. Haftaya görüşmek üzere. Bye bye. Oh, sorry. Let me stop recording.